Hey everyone, I had a request to go over the homework for Chapter 6. Um, there are two separate parts, and I will be going through both parts. On the Part 2 questions, I did end up getting rid of one of the homework questions because upon looking at it more, it didn't make any sense, so I apologize for that. Let's go ahead and start with Part 1. The first question is to calculate the frequency of light having a wavelength of 519 nanometers. So when it comes to electromagnetic radiation or light, we know that the speed of light is equal to our wavelength times frequency. But our wavelength needs to be in meters, so we can convert that to meters if we to start. So we have 519 nanometers, and there's 1 meter for every 1 times 10 to the 9th nanometers. So this gives us 5.19 times 10 to the negative 7th meters. You could also write it and just put 519 times 10 to the negative 9th meters. They're the same thing, just proper scientific notation or not. It doesn't matter though. All right, so then we can solve for nu, or frequency here. Let's divide both sides by lambda. So nu is equal to c over lambda, and c is equal to 2.998 times 10 to the 8th meters per second, divided by 5.19 times 10 to the negative 7th meters. So we see meters cancel, and we're left with inverse seconds. So we get 5.77 times 10 to the 14th inverse seconds, or hertz. Hertz and inverse seconds are the same thing, which you will see on the next one. We're told a typical frequency used by GSM cell phones is 581 megahertz. What is the wavelength of this signal? So just like before, c equals lambda nu. In this case, we want wavelength, so lambda equals c over nu. And we have 581 megahertz. So we need to go ahead and turn this into hertz, which is the same thing as inverse seconds. So mega means 1 times 10 to the 6th hertz for every 1 megahertz. And then you can also say there's 1 inverse second for every 1 hertz. So megahertz cancels, hertz cancels, we're left with inverse seconds. So this is 5.81 times 10 to the 8th inverse seconds. Or you could also just write 581 times 10 to the 6th inverse seconds. Either way works. So then lambda is equal to 2.998 times 10 to the 8th meters per second, divided by 5.81 times 10 to the 8th inverse seconds. Seconds cancel, we're left with meters. So this gives us but if you look at the answer, to type it in on ChemVantage, it wants your answer, it does want it in meters, just kidding, ignore that last part. So then lambda is equal to 0.516 meters. All right, number 3 is where it starts to kind of pick up the difficulty a little more. It says to calculate the wavelength of light emitted from a hydrogen atom when it undergoes a transition from the n equals 9 level to n equals 3. So this is going to be needing the Rydberg equation. And one thing the Rydberg equation tells us is that n1 is less than n2. So then in this case, n1 is going to equal 3, and n2 is going to equal 9. The Rydberg equation is 1 over lambda is equal to the Rydberg constant times 1 over n1 squared minus 1 over n2 squared. So we're going to go ahead and just solve for 1 over lambda, and then we'll fix it at the end. So then plugging in what we know, the Rydberg constant is 1.097 times 10 to the 7th inverse meters times 1 over n1 squared, so that's 1 over 3 squared minus 1 over 9 squared. So then this becomes 1.097 times 10 to the 7th inverse meters times 0.09877 So 1 over lambda then is equal to 1.083 times 10 to the 6th inverse meters. Notice for n, there's no units, so we just have the units from the Rydberg constant. So to get rid of this as 1 over lambda, we need to take the inverse of everything. So we're going to put everything to the negative 1 power, or do 1 divided by everything. So then that tells us that lambda then is equal to 9.230 times 10 to the negative 7th meters. But the ChemVantage wants your answer in terms of micrometers. So make sure you're looking at the answer part. And there's 1 times 10 to the 6th micrometer for every 1 meter. So this is not 0.9230 micrometers. Or micrometers, depends who you ask. Our next question, if the uncertainty and velocity of an electron is 4.10 times 10 to the 3rd meters per second, what is the minimum uncertainty in its position? So if you see uncertainty, this means we need Heisenberg's uncertainty principle. Heisenberg, which tells us that delta x times m delta v is greater than or equal to h bar divided by 2. We know delta V already, since we're told it's 4.10 times 10 to the 3rd meters per second. And we also know the mass of an electron, and that is equal to 9.109 times 10 to the negative 31st kilograms. And we want to use kilograms here because that's our SI unit, and Planck's constant H uses joules, which have kilograms in them, which we'll look at that in a second. So let's go ahead and look at h bar, which is equal to Planck's constant divided by 2 pi. Planck's constant is 6.626 times 10 to the negative 34th joules times seconds divided by 2 pi. So then h bar is equal to 1.055 times 10 to the negative 34 joule seconds. So now from our original equation, we can say that delta x has to be greater than or equal to h bar divided by 2m delta v. So we had to divide both sides by mass and delta v. And so then we can go ahead and plug and chug. Since we know h bar is, since we solve for that, we have 1.055 times 10 to the negative 34th. And a joule, just to kind of show you, 1 joule is equal to 1 kilogram times meters squared per second squared. And I'm going to rewrite this a little bit so it's easier to see the units canceling out. Kilograms times meters squared times, and I'm putting seconds to the negative 2 because that means 1 over second squared. And then times seconds, since it's a joule second, divided by 2 times our mass, which is 9.109 times 10 to the negative 31st kilograms, times delta V, 4.10 times 10 to the 3rd meters per second. We can say meters times inverse seconds. So we can see 1 second goes away here, gets rid of the squared, and then these guys cancel out. One of the meters cancels out. We're left with 1 meter, which for our units, which is good because we're looking at position. X means position. So that M tells us meters, perfect. So when you plug all this into your calculator, we get 1.412 times 10 to the first power. Or I'm sorry, no, not to the first power, I can't read my own writing sometimes. .412 times 10 to the, I think it's the negative 8th. Let me double check on my calculator. We have to change the units to nanometers. So, yeah. 1.055 e to the negative 34 divided by 2 divided by 9.109 e to the negative 31 divided by 4.10 e to the 3rd 10 to the negative 3 6, 7, 8. I was right. 10 to the negative 8th meters. But ChemVantage wants us in terms of nanometers. So we have 1.412 times 10 to the negative 8th meters times 1 times 10 to the 9th nanometers for every 1 meter. And this gets you 14.1 nanometers. This question is very picky on sig figs, so they want 3 sig figs. Okay, so just keep an eye on that. It might be a significant figure issue here. Okay, number 5 tells us to calculate the de Broglie wavelength of a helium atom moving at a speed of 213 meters per second. So the de Broglie wavelength, lambda, is equal to h over mv. We're told v is 213 meters per second. And we have a helium atom. So the mass of a helium atom, if you go to the periodic table, just look at helium, it's equal to 4.0026. And we could say grams per mole, but this is actually, we're going to say AMU. So that's the other atomic mass unit, which we talked about before. So AMU. And there actually is a way to convert AMUs to grams and or kilograms. 1 gram is equal to 6.022 times 10 to the 23rd AMU. Look familiar? Okay. And then we have 1 kilogram per every 1,000 grams. So this helium atom has a mass of 6.647 times 10 to the negative 27th kilograms. And then we already know H is Planck's constant, so we can just plug and chug here. So lambda is equal to 6.626 times 10 to the negative 34th for Planck's constant. Joule seconds, so we have kilograms times meter squared times inverse second squared times seconds, divided by our mass, which is 6.647 times 10 to the negative 27th kilograms, times our velocity, 213 meters times inverse seconds. So we can see our units canceling out, and we're left with meters for our wavelength, which makes sense. So we get 4.68 times 10 to the negative 10th meters. Our next question, calculate the wavelength of a photon emitted when the electron in a lithium plus 2 ion relaxes from the n equals 4 energy level to the n equals 2 energy level, and use Bohr's model of the atom. So lithium 2 plus is one of these 1 electron atoms that can somewhat behave like a hydrogen atom, but it has a different weight because it still has more protons. So we have to use its nuclear charge. So this is where we're told the equation En is equal to kz squared divided by n squared. So we need to use this equation. We have two n's. We have n1 equal to 2 and n2 equal to 4. And so we have a delta E. So our delta E here is going to equal E1 minus E2, the electron from N1 minus the electron energy from E2. And so that would be kz squared over N1 squared, N1 squared minus kz squared over N2 squared. And this might look kind of familiar. We can factor out that kz squared, because that's the same for both. Then that gives us kz squared times N1 squared minus 1 over N2 squared. Now the next thing we can go ahead and look at is delta E. Okay, is also equal, whoa, that's a weird. Delta E is also equal to HC over lambda. So now we can say HC over lambda is equal to kz squared times 1 over N1 squared minus 1 over N2 squared. We're solving for lambda, so let's go ahead and get 1 over lambda by itself by dividing both sides by HC. So 1 over lambda is equal to K z squared divided by hc times 1 over n1 squared minus 1 over n2 squared. And k over hc is equal to the Rydberg constant. So now we can say that this is equal to r infinity z squared times 1 over n1 squared minus 1 over n2 squared. So this just kind of saves us a little bit of work. You can always do each of these parts separately and then come together with them, but I'm a math girl, so I like being able to derive these equations. It might even come in handy on the midterm, I can't say for sure, but just to have this kind of final form of the equation. So now we can start plugging and chugging. So the Rydberg equation is equal to 1.097 times 10 to the 7th inverse meters times z squared, the effective nuclear charge, or the nuclear charge, not effective, sorry, of lithium 2 plus for lithium. Z is 3, so we have 3 squared times 1 over 2 squared minus 1 over 4 squared. So now we have 1 over lambda is equal to 9.873 times 10 to the 7th inverse meters. I'm taking Rydberg, multiplying these two, times 0.1875, looking at the ends. And this is equal to 18511.875 inverse meters. So like before, we need to take the inverse now to get that lambda is equal to 5.40 times 10 to the negative 8th meters. But ChemVantage wants your answer in nanometers. So we have to multiply this times 1 times 10 to the 9th nanometers for every 1 meter. And then we get 54.0 nanometers. So it doesn't matter what numbers you were given for your energy levels. I'm assuming most of you were given lithium 2 plus, but if not, your book tells you what the charges to use for some of the other ions. Okay, our next question. A hydrogen atom initially in the n equals 9 quantum state emits a photon having a wavelength of that. What is the quantum number of the final state of the atom? Now, since it's emitting a photon, that means we're going down in energy level. So we're going to go ahead and say that this n equals 9 is n2, since n1 needs to be smaller than n2. We don't know n1, but we know our lambda, and we also have the Rydberg equation. And since it's hydrogen, we don't have to worry about the z squared. So we can just say 1 over lambda is equal to r infinity times 1 over n1 squared minus 1 over n2 squared. We need n1. So the first thing we should do is divide both sides by r infinity. So now we get 1 over r infinity times lambda is equal to 1 over n1 squared minus 1 over n2 squared. Add n2 squared to both sides. So 1 over r infinity times lambda plus 1 over n2 squared is equal to 1 over n1 squared. Now we need to take the square root of both sides. I'm going to just kind of switch my sides of my equation just because. So now we have 1 over n1 squared, the square root of that, is equal to the square root of 1 over r infinity lambda plus 1 over n2 squared. And then the last thing is we need to take the inverse of it to get that n1 up top. So we end up with the final equation that n1 is equal to, in parentheses, square root of 1 over r infinity lambda plus 1 over n2 squared, and the inverse of that whole thing. So let's go ahead and take this step by step. So first things first, let's look at the inside of the square root. So that tells us we have 1 over r infinity, which is 1.097 times 10 to the 7th inverse meters, times our lambda, which is 0.922658 times 10 to the negative 6 meters. Wanted to do all that first before I put 1 over the whole thing. We can see the meters there cancel. Plus 1 over n squared, or n2 squared, which is 1 over 9 squared. and this whole thing in parentheses to the negative 1. So then this gives us square root of 0.0111 to the negative 1, which is 0.3333 to the negative 1, which gives us a final answer of 3 when you take the inverse, or when you do that to the negative 1, which makes sense. It needs to be an integer. Remember, for our energy levels, you can't have a fraction. The energy is quantized. It has to be a whole number. So this goes to n equals 3. You can always do this numerically, put in what you know and solve for things one at a time. But like I said, I like to derive equations so I have a final form and then plug everything in. But it's really up to you how you want to do that. Okay, calculate the characteristic wavelength of an electron traveling at 5.29 times 10 to the 5th meters per second. So this is a de Broglie wavelength question. Lambda is equal to h over mv. V, we're told, is 5.29 times 10 to the 5th meters per second. We know h, we know the mass of an electron, 9.109 times 10 to the negative 31st. So this is a nice plug and chug for us. So lambda is equal to 6.626 times 10 to the negative 34th kilograms times meter squared times inverse second squared times seconds divided by 9.109 times 10 to the negative 31st kilograms times 5.29 times 10 to the 5th meters per second. Oops. I don't know why I keep doing that. Okay, so that leaves us with meters. And you get 1.38 times 10 to the negative 9th meters. Okay, our next question. How many electronic orbitals exist for a hydrogen atom having n equals 2? So the theoretical way of going about this, so n equals 2, so then that means that L can be equal to 0 or 1, and then our m sub L can be 0 at L equals 0, and at L equals 1, it could be negative 1, 0, or 1. So this gives us a total of 1, 2, 3, 4 orbitals. The really quick, easy way is that the number of orbitals is equal to n squared, 2 squared, 4. Either way, you get the same answer. It just depends on if you want to know what those orbitals are or where they are, how it works. Okay, number 10. No object can travel faster than the speed of light. What is the minimum uncertainty in the position of an electron, given that we know nothing about its speed except that it is less than the speed of light? So we see uncertainty, boom, Heisenberg uncertainty principle. So delta x times m delta v must be greater than or equal to h bar over 2. And earlier we calculated h bar and found that it's 1.055 times 10 to the negative 34th joules times seconds. So solving for delta x, it must be greater than or equal to h bar over 2m delta v. So then that's 1.055 times 10 to the negative 34th kilograms times meter second times inverse second squared times seconds divided by 2 times 9.109 times 10 to the negative 31st kilograms times 2.998 times 10 to the 8th meters per second. So we're using the maximum speed because this is an uncertainty. So we're going to use that as our uncertainty and saying that our uncertainty in the position has to be at least this number because we don't know anything about the speed. So we know the maximum speed, the maximum uncertainty of its speed is the speed of light. So meter squared, meters, seconds all cancel, kilograms, kilograms, we're left with meters. So then we get that delta x must be greater than or equal to 1.93 times 10 to the negative 13th meters. So I think for that question, it's more of a wordage problem. It's just kind of worded weird. Okay. So part 2 now. This first question is kind of bizarre, but it's a good theoretical question. So I want to first stress that this is not how it actually works. So we're told if the energy of atomic orbitals in many electron atoms depended only on the principal number n, as it does for 1 electron atoms, how many unpaired electrons would there be in element 21? So this means we're going to basically ignore the fact that there's s, p, and d orbitals. Okay, well, there's going to be n equals 1, n equals 2, n equals 3, but we're just going to pretend that there's no, again, s, p, d, f. So in the first, at n equals 1, can handle 2 electrons. And at n equals 2, in the SPD world, there's 2 electrons plus 6 from the p shell that we're looking at, so that's 8 electrons. So that means in total we have 10 electrons in n equals 1 and 2. So that means 11 must be in n equals 3. So since this is n equals 3, then n squared tells us that we have 9 orbitals. So we're assuming these orbitals are degenerate and every single one has the same energy. So not like the s, p, and d orbitals. We are just assuming all 9 of them are the same. So because I'm a visual person, let's draw a little orbital diagram. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 11 electrons. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we have to go 10, 11. So we have 2 sets paired and 1, 2, 3, 4, 5, 6, 7 electrons that are unpaired. So 7 unpaired electrons. So that's what this question meant. I hope this makes sense to you guys. I know it's kind of a weird question. If it doesn't seem clear to you, just let me know. But just remember, this is hypothetical. It's not really what happens. Okay, this is a better question. How many unpaired electrons are there in a ground state atom of element 44 if the charge on the atom is positive 7? So if we look up element 44, oops, this is ruthenium. Okay, so ruthenium then has an electron configuration of krypton, and then it goes 5s1, 4d7. And your book gives this to you. If you look in the periodic table, it gives you the, in this chapter, it actually gives you their neutral electron configuration. So if it's plus 7, then that means we're getting rid of 7 electrons in the outermost shell, which would be this d, which would be the 4d, and that's all of them. So that means it's going to go away, and we're going to be left with Kr 5s1. And so then that tells us then there's 1 electron in this outermost shell now. So that's 1 unpaired electron. Make this a little more clear. There. Okay. And the last question, again, I got rid of the 4th question, so this is the last one now. What is the atomic number of the neutral atom having the excited electron configuration of that? Now notice there's no positive charge, there's no negative charge, so this tells us this is still its electron configuration. So we need to actually figure out the total number of electrons. So xenon, since that's our base here, has 54 electrons. And then we have 1 electron in the in 6s1, 10 electrons in 4f10, and 10 electrons in 5d10. So this adds up to be 75 electrons. This is a neutral charge, so that means that 75 is our atomic number. And this is rhenium.